All right, so we're going to go over E3.5, which is domain and range. We're not going to do a whole lot with range. I'm just going to refresh how to find the range looking at a picture, but we are going to do some more complicated examples of how to find domain based on what we know of domain and range that we went over last time. Okay, so let me just remind you, when we talk about domain, what we're talking about is the set of all inputs. Okay, whatever we can put into the function, which is normally our x values. Okay, the set of all x values, or the set of all inputs. So these are the values that can be plugged in and not cause problems. That's the best way to say it. Okay. Sometimes when we plug values in, we get undefined, we get things we can't evaluate with real numbers, that type of thing. So when we talk about the domain, we're talking about the set of all input values that it's okay to put into the function, because they're values that when we put them in, we don't have problems. We can evaluate them and simplify and so on and so forth. Okay. So the things that we look for are for radicals and for denominators. Okay. So when we look at radicals or roots, okay, even roots give us a problem. Even roots would be like the square root of something, or the fourth root of something, or the eighth root. Okay, whatever this little number here, whatever the root is, it's even. Okay, so when we're dealing with even roots, meaning our little number there is an even sign, whatever's underneath the radical, which we call the radicand, has to stay positive. Because remember, we can't evaluate a negative under an even root, because that comes out as an I, right? And I's we can't graph, we can't do anything with. So for this case, whenever we have even roots, we know that the radicand, which remember is what's underneath the radical, has to be non-negative. And the way that we say non-negative is we say it has to be greater than or equal to 0. Okay, so anytime we see an even root, we take what's underneath it and we set it greater than or equal to 0. Okay. Now odd roots are a little bit different. If I had something like the cube root of something, remember with odd roots we can evaluate positives, we can evaluate 0, we can evaluate negatives. We have no problem taking an odd root of any kind of number. So anytime you see an odd root, we just don't worry about it. Okay, there's no restrictions. Okay, and anytime there's no restrictions, that means that our domain would be all real numbers, or negative infinity to positive infinity. Okay. Now, there may be an odd root and something else. If you have another problem, you still need to accommodate for it. But if all you have is an odd root, then you don't have any problems. Okay. And then the other thing we look for is denominators. Anytime we have a rational expression, okay, remember the top is called the numerator and the bottom is called the denominator. Okay. Anytime we have rational expressions, the denominator cannot equal 0, right? Because 0 on the bottom of a fraction is undefined. We can't take a certain number of parts and divide it into 0 pieces, right? If we have a certain number of parts, we need to at least have that many parts as a total. So if the 0 is underneath the fraction, it's undefined. So anytime we're giving a denominator that has a variable in it, we set that denominator equal to 0 and solve for the excluded values. Okay, so I'm just going to say here, let's see, set denominator equal to 0 and solve for excluded values. Okay, so what that means is once you find these numbers, when you set the denominator equal to 0, the answers you're going to get are the values that make the denominator 0, which we know we cannot use. So once we find those values, then we just say x cannot equal whatever they are. Okay. All right, and then our range is the set of all outputs. Set of all outputs. Okay, or in other words, our y values. So when we plug in all of our inputs that don't cause problems, all of our outputs are that set is our range. Okay. All right, so I'm going to look at a few pictures finding domain and range just based off of a graph. Okay, and I just want to remind you, when we look at domain, because that's our input or x values, domain is left to right. How far to the left can I go? How far right can I go? And then to find range, I look at my lowest y value up to my highest y value. Okay. So here on this one, if I look for my domain, the furthest to the left this is going to go is negative infinity, because notice that arrow keeps going to the left, on and on and on and on and on, right? And also it keeps going to the right, on and on and on and on and on. So it's going to go from negative infinity to positive infinity. My range is a little bit different. Remember, domain was on my x, my range is my y. My lowest y value in this case, it stops here. Even though it has an arrow, this line has a zero slope. It's not angled down, right? So it's not going to get any lower than that point, and that point is -3. So I'm going to use -3 with a bracket up to my highest y value, which again here is not increasing. It stops at this exact value, which I believe is -7. I'm sorry, +7. +7. Okay. So domain keeps going in both directions, negative infinity to positive infinity. My range is my lowest y value, which is -3, to my highest, which is 7. Okay. Let's look at another one. Same thing here. Remember, domain is on my x's. The furthest to the left I can go and still have a picture for my x's is this point right here. Okay. So if I count over to the left, that's going to give me a value of -8. So -8 with a bracket is the furthest I can go to the left. And we always use a bracket unless there's an open circle. If there's an open circle, we use a parenthesis because it's not included. But anything else, we assume it's included. Okay. The furthest to the right I can go, these arrows are going to keep going and going and going. And if they keep going, that means my x's will always be defined to the right. So -8 to infinity. Then when I look at my y's, I'm looking at my lowest y value to my highest. Again, these arrows are going to keep going. So the arrow on the bottom is going to keep going south. The arrow on the top is going to keep going north. There's no stop or start point. So it's going to be from negative infinity to positive infinity. Okay, let's look at a couple more. This next one has gaps. Don't let the gaps scare you. Okay. Domain, again, remember, is our x, so left to right. So if I look to the left, notice this line up here in the second quadrant is going to keep going to the left. So negative infinity is how far I can go to the left. And then as I start going right, notice I hit a stopping point. The stopping point has an x value of -2. I'm going to include it with a bracket, and then notice my graph starts up again over here at x equals +2. So I need my little union symbol and then a new interval notation for that second piece. So the second piece starts at 2, and then it's going to keep going on out to the right. Okay, so from 2 to positive infinity. Now we do the same thing with my y's to find my range. My lowest y value, notice this line in the fourth quadrant is going to keep going down and down and down. So that means I can go all the way down to negative infinity. Now as I start at negative infinity and start going up, I have a stopping point on my y-axis right here, right? I can go from negative infinity up to this point where this piece ends, which is a y value of -5. Okay, I'm going to use a bracket. And then my y's pick up again at this piece up here, right? Now something different about this piece is, again, it has a zero slope, which means there's no increase or decrease, so that line is horizontal. And that line is at y equals 7. Now I'm not doing from 7 up to a higher value, it's just 7, right? So if it's just one number, we use set notation. So my y's can be from negative infinity to -5 or 7. And then I want to look at this rectangle one. Same thing. My x's are my domain. The furthest to the left I can go is -3. The furthest to the right I can go is over here at 4. Okay. Y's, I look at my lowest y value up to my highest. My lowest y value, excuse me, right here is -6. And my highest y value up here is going to be +9. So my range is from -6 to 9. Okay, so we've done these before with the pictures. What we're going to do now is we're going to look at how to find just the domain, not the range, just the domain when we're given a function. Now, just like we went over at the beginning of this section, when we look for domain of a function, we're only worried about two things. Remember, odd roots we don't have a problem with. They can have negatives and all that, so they're fine. The only two things I'm looking for is a denominator, because the denominator can't be 0, or an even root, because even roots, they have to have non-negative radicands. Okay, so for each of these, I'm only looking for, do I have a denominator or do I have an even root? If so, we have to figure out what the restriction is. If not, then we have no restrictions and it's all real numbers. Okay, so we're only finding the domain and we're writing our answer in interval notation. Okay, so for this first one, I have the square root of 3x minus 12. Okay, and I look, do I have a denominator? Here I do not, so I don't have to worry about that. The second thing I look for is, do I have an even root? And I do. This is a square root, right? If there's not a number written there, it's an implied 2. This is a square root, so since it's a square root, I know that my radicand has to be greater than or equal to 0, because it can't be negative, because I can't do the square root of a negative number. Okay. Now here my x is just to the first power, so I can isolate it just like I would if this was an equal sign. So I'm going to move my 12 to the other side by adding. So I have 3x is greater than 12, and then I divide off my 3, which gives me x is greater than or equal to 4. Okay. Now from here, some of y'all will be able to go ahead and do interval notation. That's fine. I suggest graphing it just to make sure if you have issues. So I'm going to go ahead and graph. If I wanted to graph this, I would put 4 on my graph. Since it says greater than or equal to 4, I would shade to the right, and I'm including 4, so I would use a bracket or a solid dot if y'all use dots. Okay, so if I want to write interval notation for what I've shaded here, notice the furthest to the left I can go is 4 with a bracket, and the farthest to the right I can go is going to be positive infinity. So that is the domain of this function. Okay, let's look at the next one over to the right here. I look for, do I have a denominator? Yes, here I do have a denominator, 6x plus 1. What we know about denominators is they cannot equal 0. So I'm going to go ahead and solve this to figure out what x value makes that denominator 0, and then disinclude it. Okay, so I'm going to move my 1 to the other side, which gives me 6x can't equal negative 1, right? And then I divide off my 6, which means that x cannot equal negative 1/6. So I found my denominator restriction, then I look, do I have an even root? Here I don't have any roots, so this is the only restriction I have. If I were to graph this, okay, wherever negative 1/2 is on my graph, I'm going to put an open circle because I'm saying I cannot include that value. But it can be anything else. So I would shade on the left side of that value and on the right side of that value. And then I would write interval notation. So this goes from negative infinity up to negative 1/6, and then we're not including it, so I use a parenthesis. And then on the other side of negative 1/6 on out to positive infinity. Make sure you use parentheses on your negative 1/6, otherwise you're including it. Okay. All right, let's look at this next one. I have the square root of x plus 2 all over x minus 1. First thing I look for, do I have a denominator? Here I do. I have x minus 1. Denominators cannot equal 0. So I go ahead and solve this. If I move my 1 over, that tells me x cannot equal 1. So I'm going to go ahead and graph that part. So wherever 1 is here, I'm going to put a circle and say it cannot equal 1, just like I did on the last one. Then I look, do I have an even root? Here I do, right? If I have an even root, then whatever's underneath here has to be greater than or equal to 0. It has to stay positive or 0. It can't be negative. So I'm going to go ahead and write down here. That means that x plus 2 has to be greater than or equal to 0, which if I move my 2 over, this tells me x has to be greater than or equal to negative 2. So I'm going to go ahead and put negative 2 on my graph. Since I have that equal to bar, that means it's included. Okay, so you can use a solid dot or a bracket, whichever one you want. Okay, and if it's greater than, that means I'm shading to the right. So I'm going to start shading to the right, and I encounter 1. Remember, 1 cannot be included because it makes the denominator 0. So I'm going to hop over to the other side of 1 and keep shading. So what this means in terms of my interval notation is that the furthest to the left I can go is negative 2, and then as I travel to the right, I can only go up to 1, where then I have to take out 1 with a parenthesis, and then on the other side of 1, I can go on out to infinity. Okay. So in this case, we had both restrictions. If we have both restrictions, we figure out what would the solution for one restriction be, what would the solution for the other restriction be, and then we take the most restrictive combination of the two, okay? Because it has to satisfy both, okay? All right, let's look at this next one to the right. I have cube root of 4x. Okay, so anytime I have a root, I always look at the index, or the number that is the root here. So here, this is a cube root. That is an odd number. Remember, with odd roots, we have no restrictions. No restrictions. So if I have no restrictions and a cube root is all that I have, then my domain is going to be all real numbers. All real numbers in interval notation is negative infinity to positive infinity. Okay, let's look at another one. Okay, on this next one, I look, do I have a denominator? Which I do. Denominators cannot equal 0. So I'm going to go ahead and solve this one. Now here I have an x squared, which is a little bit different. If I have an x squared, that means that I have to do some product, I have to factor it, use a quadratic formula, do something to figure out what the values are that solve this. So I'm going to try some product first. Here I would have a sum of -6 and a product of 8. So to multiply to get 8 and combine to get -6, I would use -4 and -2. And since my leading coefficient is a 1, then that means I can use the shortcut. Anytime the leading coefficient is a 1, the numbers I find in my chart are my factors. So this means x minus 4 times x minus 2 cannot equal 0. And then I just solve each one. So x minus 4 can't be 0, x minus 2 can't be 0, which means that x cannot equal positive 4 and x cannot equal positive 2. So if I wanted to graph this, I would put 2 and 4 on my graph, and I would just put open circles at both of them because I'm not including them. Now once I have that down, then I can shade everything else. So I can shade to the left of 2, in between 2 and 4, and to the right of 4. So that means I'm going from negative infinity to 2 with a parenthesis, take 2 out, then go from 2 to 4, take 4 out, and then go from 4 to infinity. Okay. I didn't have an even root on that, so the only stipulation are the values I need to exclude from the denominator so that it doesn't equal 0. Okay. And I will go ahead and mention, a lot of people think that when I say the denominator can't equal 0, they take that as x cannot be 0. That's not what I'm saying. What I'm saying is we're finding the values that make the entire denominator 0. So in this case, the numbers that make the denominator 0 were 2 and 4. So those are the only two numbers I have to take out. Okay, here x can actually be 0, because notice if I plug 0 into my denominator, my first two terms would become 0 and it would just equal 8, which is completely fine. Okay, so we're not saying it can't equal the number 0. We're saying let's find the values of the variable that make the entire denominator 0, and that's the values we have to exclude. Okay, all right, let's look at another one. On this one, I look, do I have a denominator? Yes. Okay, denominators cannot equal 0. So I need to solve to make sure this is not equal to 0. And then notice I also have an even root. So when I have even roots, that means that 3x minus 12 has to be greater than or equal to 0. Now, added stipulation here, because I just said it can't equal 0. So if it can't equal 0, then when I do the radical, solving for it to be greater than or equal to, since I just said it can't equal 0, then I'm going to take out this equal to bar, okay, and make this just strictly greater than. Since it happens to be in the denominator, denominators cannot equal 0, so for this particular radical, it not only has to remain positive, but it can't be 0, because if it's 0, we get a 0 in the denominator, which we can't have. Okay, so I'm going to solve this as 3x minus 12 is strictly greater than 0. So I move my 12 to the other side, which says that 3x is greater than 12, and then I divide off my 3, which says that x is greater than 4. Okay. If I wanted to graph this, I would put 4 on my graph. It has to be greater than 4, so I would shade to the right. And I'm not including 4, so I would use an open circle or a parenthesis. Okay, so interval notation from this one would be 4 with a parenthesis, because we're not including it, out to infinity. Okay, and notice the reason we're not including 4 is, notice if I were to plug 4 back into my denominator, 3 times 4 is 12, minus 12 is 0, Square root of 0 is 0. We can't have 0 in a denominator. So for this instance, because the radical was in the denominator, we do it strictly greater than 0 instead of greater than or equal to 0. Okay, that's the only time we use strictly greater than. If the radical is its own term or it's in the numerator, then we can include the 0. Okay. All right. I'm going to look at a few more. So the only difference on the next few examples here in a minute is, remember in section 3.5, or 3.4 rather, we had to find the intervals. We had to find the zeros and test the intervals and see if they were positive or negative. And then depending on our inequality sign, we took either the positive or the negative intervals. We're going to have to use that here to find domain. Okay, so I'll show you how that's incorporated here in just a minute. This first one doesn't use it. So this first example on the top left-hand side of page 3, I look at each piece. Notice this first piece is a cube root. If it's a cube root, it's odd, so it has no problems, okay, or no restrictions. So I look at the next term. The next term, I have an x. If I have an x, that's a denominator. Okay, remember our denominators cannot equal 0, which in this case means x cannot equal 0. Okay, there's nothing left to solve for, it's just an x. And then my last term is just a 2. It doesn't have a denominator, it doesn't have an even root, so we have no restrictions. So our only restriction here is that x cannot equal 0. So wherever 0 is on my graph, I would put an open circle there, and it can be anything else. So that means it can be from negative infinity to 0, and then on the other side of 0 on out to infinity. Okay, with parentheses because we're not including 0. All right, so this next one is going over what I just talked about. Here we have an even root. We know that even roots have to be greater than or equal to 0. Now, in order to solve this, on all the other ones, we just isolated x, right? We just moved the 4 over. But here I have an x squared. Okay, if I have an x squared, I cannot solve this using the square root. Okay, I'm going to write this, don't write this. But if you have x squared, I can't just move 4 to the other side and do the square root. I can't say x is greater than or equal to plus or minus 2. That's bad math, okay? We can only do the square root property if we have an equal sign, okay? Not inequalities. So the way that we solve this is we solve this the same way we did our last lecture on 3.4. I'm going to go ahead and say x squared minus 4 is greater than or equal to 0, and I'm going to factor this to find the zeros. This is a difference of squares, so it factors into x plus 2 times x minus 2. And then to find, I'm going to just use an equal sign for now to find the zeros. When I set each of these equal to 0, x plus 2 equals 0, x minus 2 equals 0, that gives me negative 2 and positive 2 as my zeros. So just like we did on 3.4, I'm now going to put negative 2 and 2 on my graph, and I'm going to test these intervals to see which ones are positive and above the x-axis, and which ones are negative or below the x-axis. Okay? So I'm going to pick a number in between each little 0. So to the left of negative 2, I'm going to pick negative 3. In between negative 2 and 2, I'm going to pick 0. And then to the right of 2, I'm going to pick 3. And I'm just going to test these by plugging them in. And I'll go ahead and say, you can plug them into the original here, or you can plug them into the factored form, whichever one is easier. Okay. In this case, I think it's just as easy to plug it into the original. So that's what I'm going to do. So I'm going to go ahead and box that in so you know where I'm plugging them in. So if I plug in x equals negative 3, negative 3 squared gives me 9, minus 4 gives me 5, which is a positive number. So that means that this is a positive interval. Okay. When I plug in x equals 0, 0 squared is 0, minus 4, which is negative 4. So this is a negative interval. And then I plug in my last test point, x equals 3. 3 squared is 9, minus 4 gives me 5. So this last interval is positive. Okay. So the reason we did this is, remember, we're trying to figure out where x squared minus 4 is greater than or equal to 0. Greater than or equal to, when we see that symbol, that tells me that I want the above, okay, or positive intervals, and I'm going to use brackets. Okay. Okay? Greater than means we want the positive intervals, or the intervals that are above the x-axis. And when it has the equal to bar, that means I'm including my zeros, so I'm going to use brackets or solid dots, however you want to think about it. Okay, so my positive intervals would be my first interval up to -2, and my third interval that goes from 2 on out to the right. Okay, which means that my solution for this function would be from -infinity to -2, and then from 2 to infinity. So the only thing that's changed is we're still taking an even root and saying we need it to be greater than or equal to 0, but instead of being able to just isolate x like we did on the other ones, we have to find the zeros, test the intervals to see which intervals are actually greater than or equal to 0, okay? And that only happens if you have a power of x that's bigger than 1. So if you have an x squared, x cubed, that's when you have to use this process. If you just have x to the first power, you don't have to go through all this. Okay, let's look at a couple more, and then I'll have y'all try some. Okay, so again, on this first one, I notice I have, right away, I have a square root, which is an even root. Even roots have to be greater than or equal to 0. So again, here I see an x squared, which tells me I'm going to have to test the intervals. So in order to do that, I need to find the zeros of this expression, and I'm going to factor it. I notice that every single term is divisible by 2, so I'm going to go ahead and take out a 2, which leaves me with x squared minus 3x minus 10 is greater than or equal to 0 is what we're trying to figure out. Where is this expression greater than or equal to 0? And now I can do some product in here, right? My sum would be -3, my product is -10, so I can use -5 and +2. Since my leading coefficient is a 1, okay, I can use my shortcut, which says that these factors are going to be the numbers inside my factor quantities. So this factors into x minus 5 times x plus 2. And I want to know, where is this greater than or equal to 0? So the first thing I need to do is find my zeros. If I set x minus 5 equal to 0 and solve, I'm going to get x equals 5. If I set x plus 2 equal to 0 and solve, I'm going to get x equals -2. And this 2 out front I don't have to worry about because it doesn't have a variable. Okay, 2 is not equal to 0. No value of x is going to change that 2 into a 0 because there's no x next to it. So I only have the 2 zeros. So I'm going to go ahead and draw my graph and put on here -2 and 5. Okay, and then I'm going to test my intervals. So I'm going to pick -3, something between -2 and 5, I'm going to pick 0, and something bigger than 5, I'm going to pick 6. Okay. So when I look at x equals -3, I'm plugging it in. Now, when I plug it in, I'm only testing for where the square root is positive. I don't care about the entire function. I'm just trying to make sure that that little piece that's under the radical stays positive. So when I plug these values in, I only need to plug them into the piece under the radical. So you can plug them into the original here, which I'm not going to do, or you can plug it into the factored form here, which is where I'm going to plug it in. Okay? Either one will give you the same answer. I think it's easier to plug it in when it's factored. So if I plug -3 in here, notice I already have just a constant 2. If I do -3 minus 5, that gives me -8. And -3 plus 2 gives me -1. Okay. If I multiply these together, 2 times -8 is -16, times -1 gives me +16. So this first one's going to be a positive interval. When I plug in 0, I still have that constant 2 out front, my greatest common factor. 0 minus 5 is -5. 0 plus 2 is 2. Again, if I multiply these together, 2 times -5 is -10, times 2 is -20. So this is a negative interval. And then when I test 6, x equals 6, again I have my constant 2 out there. 6 minus 5 is 1. 6 plus 2 is 8. When I multiply 2, 1, and 8, I get +16. So this is a positive interval. Okay. Again, here I'm looking for greater than or equal to. Greater than or equal to tells me that I want the positive intervals. Okay, I want the positive intervals. and I'm going to use brackets because it has that equal to bar. Okay. Now, one other thing I have to look for really quickly before I go ahead and make my final assumption as far as the domain is we had an even root here, but we also had a denominator. Okay. Remember, denominators cannot equal 0. So here, x cannot equal 0. So if I were going to look on my graph here, that means that I would have to put an open circle at 0. I cannot include that. Okay. So when I look at my intervals that are positive, that's from -infinity to -2, and then I use a bracket, and then it's from 5 on out to infinity. So notice the two answers I got from solving my even root don't even include 0. So if they don't even include 0, I don't have to worry about that added restriction, okay? Because 0 is not in my shaded area. If it was in my shaded area, then I would have to take it out using parentheses. But here, since it's not, I don't even worry about it. So this means my solution would be from -infinity to -2 with a bracket, and then from 5 on out to infinity. Okay. Let's look at one more, and then y'all can try some. So on this one, I look for, do I have a denominator, do I have an even root? In this case, I have both, and they happen to be in the same spot, right? I have an even root in the denominator. So normally, I would say my denominator cannot equal 0, right? And then because I have an even root, I would say -x squared plus 25 has to be greater than or equal to 0. However, since I just said it cannot equal 0 because it's in the denominator, I'm going to go ahead and get rid of that equal to bar, okay? So I need it to be strictly greater than 0, because if it equals 0 and it's in the denominator, that will give me an undefined value. Okay, so I'm going to work this one the same way I just did the last one. I'm going to go ahead and factor it so I can find the zeros, because here I have an x squared. So I'm going to take out a negative, which leaves me with x squared minus 25 is greater than or equal to 0. And now I have a difference of squares. So I have the negative out front, and then this factors into x plus 5 times x minus 5. Okay, so if I were to solve this for my zeros, my first quantity would give me x is equal to -5. My second factored quantity would give me the 0, x equals +5. Again, I don't have to worry about my greatest common factor because it's just a -1. -1 is not going to magically turn into 0 under any circumstance. So we leave it alone. So I'm going to go ahead and draw my graph, and I have a -5 and a +5, and I need to test each interval. Okay, so I'm going to pick a test point, something smaller than -5. Let's do -6. Something between -5 and 5. I'm going to pick 0. You can pick 1, 2, -2. It doesn't matter. And then something bigger than 5 would be, I don't know, here 10. Pick something different. Okay. All right. So I'm going to plug these in. Now again, when you plug them in, you can plug them into the original up here, -x squared plus 25, or you can plug it into the factored version. So I'm going to plug it into the factored version here. It really doesn't matter, whichever makes you happy. Okay. Excuse me. So I have x is equal to -6. When I plug that in, notice I already have a negative out there, and then -6 plus 5 is -1. -6 minus 5 is -11. When I multiply these together, I have 3 negatives, right? 3 negatives is going to make this a negative interval. And I'm not actually writing out what it equals. You can if you'd like. We don't really care what it equals because we're not graphing it. We're just trying to figure out if it's a positive or a negative interval. When I plug in 0, I have that negative outside of my factors. 0 plus 5 is 5. 0 minus 5 is -5. So here I have 2 negatives, which makes this a positive interval. Okay. And when I test x equals 10, excuse me, I have that negative weighting out front. 10 plus 5 is 15. 10 minus 5 is 5. Here I just have 1 negative, so that makes this a negative interval. Okay. Again, I'm looking for the positive intervals. Remember, my symbol was great. Ooh, I made a boo-boo. Don't don't make this mistake. We just said, notice here in pink I circled, the denominator cannot equal 0. If it can't equal 0, then I have to take out that equal to bar. So here I shouldn't have written it. I need to take out my equal to bars. Sorry about that. So notice, since my symbol is strictly greater than, if my symbol is strictly greater than, this tells me that I want the positive intervals, and I'm going to use parentheses because I cannot include the values that make my denominator 0. Okay, so the only positive interval I have here is between -5 and 5, and I can't include those two numbers because if I plug -5 or 5 back into my denominator, it makes it 0. So I'm going to use a parenthesis on -5 and +5, which means that my solution is from -5 to +5, both with parentheses. Okay. So I've had several students ask me, you know, if this is in the denominator and the denominator can't equal 0, then why are you including 0 in your answer? Again, I just want to reiterate, I'm not saying x cannot equal 0. I'm saying the whole denominator cannot equal 0. And here the whole denominator is that -x² plus 25. So x can actually equal 0 here, because if I plugged in 0 for x, I'd get -0², which is just 0, plus 25, which is a number that's okay to have in the denominator. Okay, the values that make the whole denominator 0 are -5 and +5. So those are the two that we have to take out, that we can't include. Okay. All right, so on the next page, or this page and the next page, there's 4 for y'all to try. 1 through 4 you should be able to do. I'm sorry, 1 through 3 you should be able to do. Number 4 is not something that I would test you on. It's just added practice at putting it all together and just trying a harder example. Okay, and we'll go over them in just a minute. Okay. All right, so here's number 1. Notice all I have is a denominator. Denominators cannot equal 0. So here we just say x plus 5 cannot equal 0. When we solve, that means x can't be -5. So all I do is take it out using parentheses. When you graph it, you can use parentheses or an open circle. Either way is fine with me. So we can go from -infinity to -5, and then -5 on out to infinity. When we look at the second one we have 2 problems, right? We have a square root and we have a denominator. Denominator, excuse me, denominator cannot equal 0. So here I just went ahead and put x cannot equal 0. And then on the numerator, we have x² minus 4 has to stay positive, so greater than or equal to 0. When I factor it, it's a difference of squares. So the zeros that I get are -2 and 2, and we're going to include them because notice my symbol is greater than or equal to. So I'm going to use brackets. And then because this was an x², I have to test my intervals. So here I tested -3, which came out positive. I tested 1, which came out negative, so I don't want that one. And I tested +3 for this last interval, which came out positive, so I do want that one. Okay. So my solution here is -infinity to -2. I'm including that one, and then 2 on. Notice here, even though I said x can't be 0, x equals 0 is not even in my shaded solution. So if it's not even in my shaded solution, I don't have to worry about it. Okay. All right. On number 3, I have an even root, but it happens to be in the denominator. Remember, the denominator cannot equal 0. So if it can't equal 0, then that means when I solve my root, I can't use the equal to bar that I normally would. Okay, it has to be strictly greater than 0. So I find my zeros, which would be +5 and -1, and here they're not going to be included because I cannot include them because they would make the denominator 0. So I'm going to use parentheses. So I need to test each interval, so I use -2, 0, and 6. Okay, -2 came out as a positive interval, 0 came out as a negative interval, and 6 came out as a positive interval, which means I want the first and third intervals, so -infinity to 1 with a parenthesis, and 5 to infinity also with a parenthesis. Okay. If you tried number 4, I'm going to go ahead and put it up here. And I want to point out really quickly, notice this first piece came from number 3. Okay, this is the same as number 3. So we already have, I'm sorry, not number 3. Yes, number 3. Sorry, this is number 3. So we have our answer from number 3 here. So notice we have our answer from number 3 here, negative infinity to negative 1 and 5 to infinity. We already know where that stays greater than 0. Okay. The second piece here is, notice that's from number 2. Okay. Now, I don't have all of number 2. I didn't have the x from the bottom, but that's okay. We know that we just want this to be greater than or equal to 0, and we already worked it out from problem number 2, and this was our answer. Okay, so the only new thing that we have to work out here is this bottom piece of my third term. Okay, because it has a denominator, I know that x minus 8 cannot equal 0, which means x can't be 8. So these are my solutions to the 3 parts. Now remember, when I find the domain, I have to take, I have to take the most restrictive combination of those 3 answers. So I'm going to write it up here just so you can see what I'm talking about. What I'm going to do is I'm going to write out all the points of all 3. Okay. So notice my points of reference here. My first one needs a -1 and a 5. My second one needs a -2 and a 2, and the last one needs an 8. So I'm going to go ahead and put all these numbers on all 3 graphs. Okay, so I have a -2, a -1, I have a 2, a 5, and an 8. 2, 5, 8, 2, 5, 8. Okay, so if I look at this first one, this first piece I'm going to do on this graph, my answer for it was negative infinity to -1, so that was up to this point, and then it was not including -1, and then it was not including 5 on out to infinity. Okay, when I look at this second piece, I'm going to graph it on this one. Okay, it was from negative infinity to -2, and it was including 2, and then it was from positive 2 on out to infinity. Okay, and then my last one just can't be 8, so I'm just going to put an open circle at 8, and then it can be everything else. Okay. So notice what we're really doing is we take the solutions for each of the 3 parts, and we're trying to figure out where do they have common shading. So notice all 3 graphs are shaded up to -2, right? So that's where I got this answer down here. Okay, they all have from negative infinity up to -2 in common, so I shade that on my solution. And then as I travel over, they don't all have from -2 to 1, they don't all have from -1 to 2, they don't have from 2 to 5, but notice from 5 on, they have in common, right? From 5 to 8, they have in common. So that's why I shaded right here from 5 to 8. And the reason I have to stop at 8 is because this third one does not include 8. Okay, so I have to stop there because not all of them have 8. But they do all have from 8 on out to infinity. Okay, so that's where this shading came from. So what all 3 solutions have in common, or the most restrictive combination of all 3 graphs, is my answer for the whole function. Okay, so that would be from negative infinity to -2, 5 to 8, and 8 to infinity. And notice all of 3 graphs included -2, so I can use a bracket there. On my 5, the first solution did not include 5, so I have to use a parenthesis there. And then my third solution did not include 8, so I have to use a parenthesis on the 8 as well. Okay? In my solution, it has to work for all 3 in order to include it. Okay? All right, so that is the end of 3.5. You have a regular My Math Lab assignment for 3.5. You also have a worksheet for section 3.5, which needs to be completed and emailed into me or faxed into me, okay? The due dates for these assignments are on your lecture schedule, which is posted under your My Math Lab course materials under the lecture schedule, or under the lecture schedule tab, okay? If you have any questions or concerns, please let me know. I'd be happy to help.